Okay, so in the last video, we basically obtained the solution of the linear quadratic regulator problem for the scalar case, and we defined what our algebraic Riccati equation is, which needs to be solved first, giving us P star. And once we have the P star, we can determine U star, which is the optimal input, as a function of P star and the state vector. Okay, in this case, because we had everything scalars, X was also a scalar. Now, let me also write down what it looks like for an nth order system. Okay, so I noticed that I haven't used any color yet. Okay, so for an nth order system, obviously we have everything as matrices. Okay, so this is our general solution. Unfortunately, derivation of this is beyond our scope at this point. But we have x dot equals, in this case, ax plus bu. X is obviously in Rn, and a and b have, let's also assume that we have scalar input, so u is still an element of R. Okay, so we have therefore the cost function j u of t is equal to integral from 0 to infinity x transpose q x, x being a function of time, obviously, u transpose ru. In fact, let me make u also the general case, which is r to the power m. Okay, so that u transpose ru is also a vector matrix expression. Okay, dt. So by the way, let me also note some terminology. If this integral is, we call it the final time, and if it's equal to infinite, we have the so-called infinite horizon problem. But this integral can also be finite. Okay, so if f is finite, not surprisingly, in this case, we call this the finite horizon optimal control problem. Okay, but in our case, we are just discussing the infinite horizon optimal control problem. Okay, so in this case, we have u star of t is equal to minus k times x, k now being a vector. Okay, and k is equal to r to the power minus 1 b transpose p star is the linear state feedback coefficients, and we have p star being an n by n matrix. Okay, and it needs to be satisfy the algebraic Riccati equation in matrix form. Okay, so P star needs to satisfy, that means it's the solution of Q plus P star A plus A transpose P star minus P star B R minus 1 B transpose P star equals to 0. Now that is the algebraic, it's still called the algebraic Riccati equation. Okay, so this is the matrix form algebraic Riccati equation. And here P star is a symmetric matrix. Okay. Now, once we do this, the new system under this state feedback, the new system under state feedback, and this is from 302, okay? So it's a combination of x star, x dot being ax plus bu, and u being equal to minus k times x. So what we have is that x dot is equal to a minus bk times x, okay? And this is your new closed loop A matrix, okay? Let me also note that the solution of this algebraic Riccati equation is often very difficult to solve analytically, okay? So analytic solution is often quite difficult. Okay, so I'm going to solve an example where we will be able to generate this solution, but you will see that it's going to require the solution of linear or nonlinear system of equations. So usually the way it's done is through numerical techniques. Okay, so let's complete this file, okay, and then I'm going to open a new file for this, okay, and then let's take a look at the example through this. Hold on, the recording actually, okay, so let's stop the recording and let me come back in a minute.